Okay, now this chapter is mainly about carboxylic acids and that look like this. But the book has also put in here another functional group that in some ways, in terms of reactivity, resembles a carboxylic acid, and that's this nitrile. Let me go ahead and draw the nitrile over here. Here's a nitrile functional group. And in some ways, that nitrile functional group resembles a carboxylic acid. The main carbon right here, this carbon atom, has 3 bonds to an electronegative atom, just like the carboxylic acid does. You can add nucleophiles to the carbonyl carbon of carboxylic acid derivatives. You can add nucleophiles to nitrile. So in this chapter, even though the chapter is mainly about carboxylic acids, it also introduces nitriles. Now here's one functional group that you know how to make. We learned how to make cyanohydrins last chapter, in chapter 18. The first reaction we showed you of ketones and aldehydes was to add HCN to those. And why would you want to do that? Well, in some cases you want to have a nitrile on your drug. I'm trying to remember, there's a common antidepressant that's got a nitrile group on there. One common thing that you want to do with cyanohydrins is after you form this bond and make this carbon-carbon bond, oftentimes you want to hydrolyze that to a carboxylic acid. And here's the conditions we're going to show you. You're going to use HCl, hydrochloric acid, under brutal conditions. Hydrochloric acid, usually 6 molar hydrochloric acid, HCl. 6 molar is like taking a bottle of concentrated acid and mixing it 1-to-1 with water, and it's still concentrated when you do that. And you do these reactions in water, and you boil them overnight, not for a minute, not for an hour, but overnight. Boy, those types of conditions do all kinds of bad stuff. SN1 reactions, E1 reactions. You got to be careful with these conditions. But this OH over here is not going to be doing any SN1. The more reactive functional group is not some SN1 thing with the hydroxy. The more reactive functional group is the nitrile, and that gets completely hydrolyzed to the carboxylic acid. And I'll draw it here. It's not really important for this transformation. The other byproduct, where does that nitrogen go? It forms ammonium chloride, which, that just gets washed away with the water when you do an aqueous workup. Okay, so remember we learned how to make these cyanohydrins in the last chapter. So I hope if I tell you that cyanohydrin, I say, how do you make that cyanohydrin? You only know one way to make those. The only way that you know how to make cyanohydrins is to take aldehydes or ketones and add HCN. But you have to make the HCN yourself. And so the complex recipe that I gave you was using sodium cyanide and hydrochloric acid. All right, there's another way to make cyanide derivatives, to make carbon-carbon bonds with cyanide, and that's simple SN2 reactions. So you should already know that you can take alkyl halides, alkyl tosylates, maybe alkyl chlorides, and do displacements, SN2 displacements. So if you have a bromide leaving group here or a tosylate leaving group there, you can add sodium cyanide. Same reagent you're using above, sodium cyanide, NaCN, white powder, put it in there, and it does an SN2 reaction. The cyanide anion will just displace that bromide. And you can do the same hydrolysis of the cyano group. So we use hydrochloric acid, really concentrated hydrochloric acid, or not quite as concentrated as you get right out of the bottle, but still, boil it overnight, and there you go. You've got a carboxylic acid functional group. Now, there's other nucleophiles that you can add to nitriles. And the ones that are interesting to organic chemists are ones that make usually bonds to carbon, but I'll also show you how to do a reduction and make a bond to hydrogen. So I'm going to show you this. When we get to chapter 23, the whole chapter is about amines. I'm going to show you this reaction again, and you're going to say, I've never seen that before. And I'm going to say, I showed you this before, and you've already forgotten it. One of the money reactions we have in chapter 23 is to take nitrile groups and convert them into CH2N groups. So if I see a carbon with an NH2 and it's a CH2 carbon, that could have come from nitrile reduction. And our secret conditions for reducing those is that lithium aluminum hydride thing. Remember that 2-step reaction sequence that we talked about? Lithium aluminum hydride, step 1. Guess what step 2 is going to be? It's going to be an aqueous workup. There you go. Now we're going to show you how to put cyano groups on benzene rings in chapter 23. You don't know how to do that directly, where the cyano is directly attached to that benzene ring. That's coming up in chapter 23. We'll show you how to do that. Now what if you want an aldehyde? What kinds of things could you do with aldehydes? Well, with aldehydes, we can make imines. You can't make an enamine here because there's no H at this alpha position, so you can't make an enamine. But we can do Wittig reactions. If you're taking the organic chemistry laboratory, you'll probably use benzaldehyde as a reagent. And so how do we do this? This is another one of these obscure reagents that you didn't use a lot, but is really valuable. We taught you in chapter 17 that you could take esters and use dibal-H to convert them to aldehydes. And it seems kind of oddly strange that you can take nitriles that have a C triple bond N and also use that same dibal-H and also get aldehydes. Boy, that is a great way to make aldehydes, is to take esters and to reduce them using dibal-H. And you can do the same thing with nitriles. This won't be that useful to, again, these will work on any nitrile group as long as there's not OHs present in your molecule. You'd have to protect those. You can reduce them to amines or to aldehydes using lithium aluminum hydride or dibal-H. Now what about making carbon-carbon bonds? Boy, I'm an organic chemist. I love making carbon-carbon bonds. We can add carbon nucleophiles to nitriles. So if you take some sort of a nitrile, again, I'm using benzonitrile as my example because it's very simple, and we add a Grignard reagent or an alkyl lithium to that. I'll go ahead and draw the nucleophilic bond here in this Grignard reagent. It's that carbon-bromine bond. That nucleophilic bond, just like the lithium aluminum hydride, can attack the nitrile. There we go. And when it does that, it's mechanistically going to make, it's mechanistically going to make this weird looking species. Just go with it. There's nothing you can really do with this except to work it up in the workup. That has 2 lone pairs on nitrogen. It's an imine anion. And then you'll have that bromomagnesium salt floating around. And this you just wait to work up. And you work it up under conditions that hydrolyze the imine. It's so easy to hydrolyze imines. I'll just write H2O workup. You don't have to add toluene sulfonic acid or something special. The workup conditions will hydrolyze the imine directly to the carbonyl. This has been used in a published synthesis of bupropion. That's a happy drug. I forgot what receptor it targets, but it's a derivative of a molecule found in Middle Eastern cat plants that they chew to get high, kind of high. Somebody's making $1 billion off a chlorine derivative of that. All right, that's carboxylic acids and nitriles in one concise chapter. And when we come back on Wednesday, boy, we are going to go at it, talking about every type of carboxylic acid derivative in the universe. A few weeks ago, I was watching this old movie, old science fiction, I don't know what you call it, horror movie, sci-fi horror movie called The Blob. I think it was some low-budget movie, one of the early ones for a famous actor, Steve McQueen. And there was one scene in this movie where there's some people that are kind of holing up in this country bumpkin doctor's office, and the blob is kind of break through the windows, and the doctor is telling the nurse in there, hey, behind you, the trichloroacetic acid. So I guess the idea is let's throw some trichloroacetic acid on the blob and maybe it will dissolve the blob. It did nothing to the blob except maybe made it mad, unfortunately. But it got me interested. Why would this doctor, some everyday family physician, have a bottle of trichloroacetic acid sitting around in his practice? That just didn't make any sense to me. So let's go ahead and talk about what is trichloroacetic acid used for. There's only a few uses. Back in the 1950s, for a brief period of time, the sodium salt of trichloroacetic acid was being used as a weed killer. Not super popular, I don't think. And there's no reason a doctor would have that in his office. And it's certainly not the sodium salt. But there is a common use of trichloroacetic acid nowadays. And that is that it's used in chemical peels. I don't know a lot about this. I suppose if you've got wrinkly, dead skin and you want to strip off all the outer layers, you treat the skin with a solution of trichloroacetic acid and it kills everything, and then the skin flakes off. Well, that looks like a horror movie in itself to me. But when I think of trichloroacetic acid, I actually didn't realize that was common in chemical peels until I typed it into Google. When I think of trichloroacetic acid, there is one thing that comes to my mind, and that is DNA synthesis. So if you've ever worked in a lab where they use PCR primers or make small oligonucleotides as tools for molecular biology or biochemistry, that is made using automated DNA synthesizers, machines that are so good at doing organic synthesis. They get 99% yield on every step. Each step takes about 1 minute, as opposed to typical reactions in an organic lab that take hours or days. And so there's a particular step in DNA synthesis that's occurring on these DNA synthesizer machines that involves trichloroacetic acid. And the synthesis of DNA, oligonucleotide strands, maybe up to 50 oligonucleotides, you can do reasonably efficiently. After you add the new nucleotide subunit, there's a protecting group on that nucleotide subunit, A, G, C, or T, and that protecting group on the 5' hydroxyl group is a triphenyl methyl ether. And this bond can be cleaved through an SN1 reaction. And somebody spent a lot of time trying to figure out what kind of group comes off easiest, but not too easy, in an SN1 reaction. So they found out that 3-phenols is good, but not just 3-phenols. 3-phenols where 2 of the phenyl groups have methoxys. This is called a dimethoxytridal protecting group, and you can easily cleave it with acid. And not just any acid. Acetic acid isn't strong enough. Trifluoroacetic acid is the most common carboxylic acid derivative we use as a reagent. That's too strong. Somebody figured out that trichloroacetic acid has just the right acidity for this step. And it is, I don't know of any other place in organic synthesis that trichloroacetic acid is used. So the idea here is you just do an SN1 reaction to take off this protecting group and reveal a reactive 5' hydroxyl. Right, the lone pairs here on this 5' hydroxyl can come along and deprotonate the trichloroacetic acid. So you end up with this oxonium ion over here. This is the oxonium ion. And that's now ready to leave and pop off, give the electrons to oxygen, and then make this extremely stable dimethoxy trityl, that's the 3-phenols on a methyl is called trityl, cation. And you need those 2 methoxy groups there. Those methoxy groups stabilize that carbocation by resonance. You can draw a bunch of resonance structures for this. And then in the last step, the trichloroacetate comes back in and traps out this cation so that it can't keep reacting further. So for whatever reason, trichloroacetic acid is the unique solution to this deprotection problem. That's the only place I've ever seen it used in the field of organic synthesis. But kind of interesting to know that that's a common reagent used for chemical peels. And it's not very good if you're being attacked by a blob. But we've made a big change here. We finished chapter 19. We covered all of chapter 19 in our last lecture on Monday. And chapter 19, if you'll recall, was about carboxylic acid derivatives, the acidity of carboxylic acid derivatives, relative to other types of functional groups, and the reactivity of nitriles, C-triple bond N, we introduced. You can add nucleophiles to C-triple bond N in a way that's very similar to adding nucleophiles to ester carbonyls or even ketone carbonyls. So now in chapter 20, we're going to talk about 5 common functional groups that are derivatives. They are considered derivatives of carboxylic acids, where there are 3 bonds to heteroatoms. So first of all, we'll talk about acyl chlorides. You know about acyl chlorides. I'm going to go ahead and fill these in. If I put a chlorine atom on there, that's called an acyl chloride. And we use those in the chapter on electrophilic aromatic substitution to do Friedel-Crafts acylations. That's actually not the most common use. The most common use of acyl chlorides, as you'll see in this chapter, is to put other heteroatoms in place of that chlorine. Okay, another functional group that may seem a little bit vague is called an anhydride. More specifically, a carboxylic acid anhydride or a carboxylic anhydride. You've seen, as far as I know, one of these before, and we'll talk about that a little bit more. But you didn't see it used for anything that's as useful as this chapter. The other types of functional groups, you've seen all of these before, even if we didn't talk about specific reactions. You've talked about esters, right? We've talked about adding nucleophiles to esters. Remember chapter 17, lithium aluminum hydride, Grignard reagents, but we didn't talk about adding heteroatom nucleophiles to esters. Then we learned about carboxylic acids in the last chapter, mainly the acidity of that OH bond. And in this chapter, we're going to teach you how to replace that OH with useful stuff. Nitrogen, halogen like chlorine, oxygens to make esters. And then the last carboxylic acid functional group that we're going to talk about is going to be amides. And so let me go ahead and draw an N here. And I'll just put R2. Doesn't matter. One of the R's could be an H. Both of the R's could be an H. Or you could have two alkyl groups on there, or aryls. And I think you're doing chemistry, if you're taking the lab with where one of the R groups is an aryl group, you're brominating a derivative, an amide derivative called acetanilide. Okay, these are the functional groups. We're going to spend this chapter learning how to convert acyl chlorides into all of these different functional groups, learning how to convert esters into carboxylic acids into acyl chlorides, back and forth. Super important for organic synthesis, super important for the field of biology and biochemistry. Okay, so in section 20.3, they talk about IUPAC nomenclature, and I've mentioned this before. I don't put IUPAC nomenclature in my exams. Feel free to read through that and learn about how to name compounds specifically. I use a program called ChemDraw, where any structure you draw, you can say, give me the name by pressing a button, and it gives you the name. But I do know the names of organic functional groups, and that's what I expect you to know. Now, if you look back at my previous exams, if you look at our problem sets that we've been working on in discussion section, I put spectroscopy problems on there. I'm not going to tell you what I'm going to put on my next exam, but if you're a gambling person, there's probably a good bet that there's going to be a spec problem on there. So what can we say about how do you identify carboxylic acid derivatives spectroscopically? One common tool that you've been learning about for identification of carbonyl derivatives and carboxylic acid derivatives is to look for that CO stretch. It's usually a big, thick peak. The peaks go downward in an IR, somewhere between 1650 and 1750. And unfortunately, it's very hard to tell what kind of carbonyl you've got just by seeing that big peak in the IR in that range. You see a big peak around 1700, it's like, well, is that a ketone or an aldehyde or an amide? Or that's hard to see. But C13 NMR is extremely good for having pretty well-defined chemical shift ranges. And so let's see how you can separate two classes of carboxylic acid derivatives, or separate the carboxylic acid derivatives from ketones and aldehydes. So you might recall that we've discussed before that if you have a ketone or an aldehyde, like this over here, where you've got R groups on each side, or an aldehyde where one side has an H, those are generally going to appear past 190 parts per million. You see a peak down there, that's a ketone or aldehyde. There's just nothing else that appears down there. Now, there's other carbonyls that have an extra oxygen or a nitrogen or a chlorine atom on there. Those are all going to appear in this region from about 155 to 185. 165 would be a typical C13 signal for an ester or an amide or an acid chloride, acyl chloride. Sometimes you'll hear me use the word acid chloride. That used to be very common, decades ago, and for some reason I still make a mistake and call them acid chlorides, but in modern terminology we call these acyl chlorides, so I apologize if I refer to those as acid chlorides. Okay, so there's this region, 185, and past 180 is kind of unusual, but 185 to 155, that's carboxylic acid derivatives. Esters, amides, acyl chlorides, that's this chapter, acyl chlorides. And we've mentioned before, CC double bonds, whether they're aromatic or not, appear about 165 to 110, and pretty much anything below 110 is singly bonded to stuff. And you're not going to know what it's singly bonded to. You're just going to know there's that many carbons, unique carbons below 110 parts per million that have only single bonds to them. All right, so carboxylic acid derivatives. Now we need to talk about the reactivity of carboxylic acid derivatives. We got a slight peak at this reactivity back in chapter 17 when we talked about Grignards and lithium aluminum hydride. So one of the themes of this chapter is we're going to talk about nucleophiles adding to carbonyls, and we've already discussed that. If you take a nucleophile and you add that to a carbonyl, like a ketone or an aldehyde, that's easy. Ketones, aldehydes, you can add to those quite easily. You know, we had our last 2 chapters ago, we talked about imines and acetals. Now, when you make an ester or an amide derivative, this is not so easy anymore. If I take the same nucleophile, like sodium borohydride, and I try to get it to add into here, it just doesn't work. Sodium borohydride isn't quite reactive enough to add to an ester. Sodium borohydride easily adds to ketones and aldehydes, but not esters. So, you know, this type of reaction over here is slower. If you want to add some sort of a nucleophile, that oxygen atom on an ester, we call this the carboxyl oxygen. This oxygen right here is called the carboxyl oxygen. And I don't know if you'll hear me refer to it, but this oxygen on the top is the carbonyl oxygen. That carboxyl oxygen is doing something to slow down the rate of addition to the carbonyl. We'll have to talk about that. And if you put a nitrogen lone pair on here, wow, now that is way slower. Boy, this is now a totally different ball game to try to get things to add into amides. That is not easy. Boy, and I'll put way slower. Way slower. It's kind of clever of nature to make all of your proteins using amide bonds instead of ester bonds. Just think if nature had accidentally made all your proteins using ester bonds, they would fall apart, you know, over a year or a month or whatever. Proteins are stable. That amide bond has a half-life of about 7 years at pH 7, just sitting around in water. Okay, so let's talk about why is it that this oxygen of an ester or this nitrogen of an amide slows down the addition to the carbonyl group. This is going to be challenging to understand. We're going to be able to use principles. We always try to go back to simple principles like electronegativity, bond length, donation, and resonance to explain things. And we're going to be able to explain this using 2 effects. So unfortunately, the oxygen and the nitrogen substituents in esters and amides have 2 opposing effects. 2 effects. One effect that speeds up the rate of addition to the carbonyl. The other effect slows down the rate of addition to the carbonyl. And so which of these 2 effects wins? I'm going to have to tell you, because you couldn't figure, there's no way you could know which of the effects is more important. So I have to tell you that. There's no way to know that. So when I talk about addition to a carbonyl, like this carbonyl carbon right here, the way to think about the reactivity of that carbonyl is to treat it like it's a carbocation. There's a resonance structure I can draw where I give the electrons to the oxygen and leave a C+ behind. Well, that resonance structure of a carbonyl is kind of like a carbocation. So I can use my same thinking to ask what happens if I put an oxygen atom, for example, on a carbocation. What does it mean to put an oxygen substituent like this onto a carbocation? There's going to be 2 different effects of that oxygen atom on the reactivity of the carbocation. One effect is an electronegativity effect. So in terms of electronegativity, the oxygen atom has lots of protons in the nucleus, and so that makes that carbocation unhappy. If I've got a neighbor that has lots of protons, positively charged protons in the nucleus, that's electronegativity, then I'm going to be pretty unhappy as a carbocation. And so that's going to increase the reactivity. That carbocation's less happy because of that neighboring electronegative group. So let me just write electronegativity increases the reactivity and the rate of addition of nucleophiles. Increases the rate of addition. So nucleophiles add faster to carbocations when there's an electronegative atom next door. But there's a second effect of that electronegative atom if that electronegative atom has a lone pair. Let me go ahead and draw out the lone pair. In fact, I'll draw it really big because those lone pairs on oxygen are screaming at me. And this is a completely different effect. The electron lone pairs are completely different from the electronegativity that's caused by the protons in the nucleus. And you know what those lone pairs are doing. Those lone pairs are donating in to this carbocation. Right? The nucleophile has to collide thousands of times in order to form a bond. The lone pairs next door don't have to collide at all. They're there all the time donating into that carbocation, basically attacking the carbocation and making it less reactive. So this resonance effect, this lone pair effect, the effect of lone pairs is that they are going to slow down the rate. Lone pair that are neighboring like that decrease the rate of nucleophilic addition. Sorry, let me write this out. And which effect wins? Is it the speeding up effect of electronegativity, or is it the slowing down effect of the lone pair? Well, it's the slowing down effect. This is more important. This is the more important effect. That's why it's slower to add to esters and amides than it is to add to ketones or aldehydes. The slowing down effect of those lone pairs is more important for oxygen and nitrogen. Now we're going to see in just a second something that's quite odd. It won't make any sense to you yet, I don't think. And that is that chlorine substituents have lone pairs and they're electronegative, but they speed up the rate of addition. Acyl chlorides are super reactive. And I'll explain that very simply in just a second. Why is chloride different from nitrogen and oxygen? So esters and amides are less reactive than ketones and aldehydes. Way less reactive than ketones and aldehydes. Let's go ahead and put some numbers on this. How much less reactive? If I were to quantitatively compare, I expect you to know the relative order for the rates of addition here. Right? Which one is fastest and which one is slowest. So let's go ahead and not only I'll give you the order, but I'll also give you some extra numbers there so you can see quantitatively. And we're going to compare everything to something that is not a carboxylic acid derivative. I'm going to give you relative rates. Whoops. Relative rates here. And I'm going to assign a relative rate of 1. We don't care what the units are. We don't care whether it's 50 miles an hour or 40 molecules per second or 4 per molar per second. We don't care about the units. We just care about the relative rates. Is one thing twice as fast or 10 times as fast as another? So let me go ahead and write out these relative rates for you. Okay, relative to an aldehyde, right? An ester is less reactive. How much less reactive? I'm going to use exponents because I can't fit all the zeros there. 100,000 times less reactive. Esters are 100,000 times less reactive. Even though the electronegativity of this carboxyl oxygen is speeding up through electronegativity, the lone pair effect is really slowing down addition to the carbonyl. So esters are 100,000 times less reactive than aldehydes and ketones. Amides are even less reactive than esters. Now we're talking, and the numbers are kind of nicely even here. 10 to the minus 10. What is that, like 100 billion times? I think that's 100 billion. I don't know what it is. Doesn't matter. It's a big number. 100 billion times less reactive, or 10 to the minus 10 less reactive. It is way less reactive than an aldehyde or a ketone. It's not easy to add to amides. Amides, those carbon-nitrogen bonds of amides tend to be stable. We'll talk about how hard it is to add to that carbonyl. And finally, if I make a carboxylate anion where there's a full-on anionic oxygen with lone pairs right next door, boy, it is hard to add to that carboxylate anion when it's negatively charged. That is hard. That carboxylate anion is not reactive. I couldn't find numbers for this, so I'm just going to tell you that it's something less than 10 to the minus 15. Now, I don't know. Does it matter whether it's 10 to the minus 16 or 10 to the minus... It is way less reactive than an aldehyde. So you can add to the aldehyde way easier than carboxylates, esters, and amides. Now let's go to the left side over here. We've got this functional group, the anhydride. It's symmetrical, so both the carbonyls have identical reactivity. If I want to add to an anhydride, anhydrides are more reactive than aldehydes. How much more reactive? They're about 10 times more reactive than aldehydes. Carboxylic anhydrides are more reactive. It's easier to add to that. There must be something about that lone pair on the oxygen that makes it, keeps it from having the same effect as an ester. And finally, we're getting to the acid chloride. And look at what I've done with this bond here. I've drawn this bond here crazily long, insultingly long, stupidly long, because I want you to remember that chlorine is in the third row of the periodic table, not the second row. And so the bonds to chlorine are long. And so yes, chlorine has lone pairs, just like oxygen and nitrogen, but those lone pairs are so far away, they just can't quite donate effectively. You can't get effective pi bond formation using third row atoms. So the lone pairs are there, but they just can't quite donate through resonance. So all you're seeing is that electronegativity effect, really. And so you get this phenomenal difference in reactivity, about 10 to the 5th higher reactivity here. Whoops, let me change back to that red color here so I have uniform. So 10 to the 5th, more reactive. So more reactive than an aldehyde. Acyl chlorides are hot. Man, those things are hot. They are reactive. Okay, so here's down below here. This is what we're going to be doing in this chapter over and over in various different forms. We're going to be substituting potential leaving groups on carboxylic acid derivatives. So I'm going to show you a bunch of examples where we've got something that can potentially act as a leaving group and be substituted. And we're going to be doing this process of acyl, nucleophilic acyl substitution is what we're going to be doing. And we're going to be replacing those leaving groups with nucleophiles. Now, I want you to remember, just because I call it a leaving group does not mean it's a one-step SN2 reaction. In every single case, without exception, with carboxylic acid derivatives, when we substitute that acyl group with some sort of heteroatom nucleophile, that's the big theme for this chapter, it's going to go through this two-step process. Step one is going to be having the nucleophile add in to the carbonyl. It's easier to add into carbonyls than it is to do SN2 reactions. It's easier. Carbonyls are just way easier to add to. Carbonyls are kind of like carbocations. So every time we're doing this, we're going to have an initial stage or even a one-step process where step one is an addition step, where we're doing addition. So step one here is going to be addition to the carbonyl, the addition step, just like I showed you the rates up above. And that's going to lead to some sort of a tetrahedral intermediate. Where the nucleophile is now bound and that leaving group is ready to get pushed out. Let me draw that lone pair on that oxygen, ready to push out the leaving group. And then in the second step, boy, this is lickety-split here. We're going to be able to push out these leaving groups. No problem. Alkoxides, no problem acting as a leaving group. Chloride, no problem acting as a leaving group. Nitrogen's a little bit harder. We're not going to talk about that a lot, specifically mechanistically what's going on. But boy, it is so easy for this lone pair to push out these leaving groups that are right nearby. Step two is really kind of like an elimination. And it's like an ionization, like part of an SN1 reaction that you might have seen before. So let me go ahead and write in here. Step two is is always fast for the types of mechanisms that we're going to talk about. Step one is the slow step. If it's hard to substitute, it's because step one is slow. You can predict the overall rate of this two-step process. Even though the mechanism involves two steps, everything that slows down or speeds up the rate of substitution for carboxylic acid derivatives is due to step one. It's due to this stuff right here. You can predict the rates of the two-step mechanism just by knowing about the rates of the first step. And that's given quantitatively up above. So I expect you to know that substitution of acyl chlorides ought to be what? 10 to the 15 faster than substitution of amides? Right? If you just put them in there and let them race each other, boy, huge differences in rates of acyl substitution. Now, again, notice how I'm calling it a leaving group. Just because I call it a leaving group doesn't mean it's an SN2 reaction. And you're going to have a tendency to think that the word leaving group only is for SN2. No, it's for things that have nothing to do with SN2. All right, let's go ahead and preview all the different functional group interconversions that we're going to see in this chapter. It's going to be mind-boggling. It's like you think you learned a lot of reactions already. We're just going to pour them onto you because that's the way organic chemistry, the field of organic chemistry works. You know, you learn, I'd say a handful of powerful recipes, but maybe it's 100 powerful recipes, and then you're ready to go make drugs and make $1 billion. So let's go ahead and talk about some of these functional group interconversions. I'm going to show you what will be the most valuable functional group interconversion that you'll see in this chapter. It's the most powerful one. It's converting carboxylic acids into acyl chlorides. You know, we talked about using acyl chlorides for Friedel-Crafts acylations back in chapter 16, and we didn't tell you how to make them. How frustrating. So let's go ahead and talk about how we're going to make them. I'll tell you now, and then I'll tell you again shortly. So our secret recipe is going to be a reagent you have seen before. It's called thionyl chloride, SOCl2. You've seen that before. But these are not the same conditions you used to convert alcohols into acyl chlorides. We don't add pyridine in this reaction. We do this using just heat. Typically, you boil it in benzene at 80 degrees for a few hours. So SOCl2 and heat. And you need to add the heat in there. You can write heat. You could add delta. You can put 80 degrees, but you need to indicate that these are not room temperature reactions. Okay, converting carboxylic acids directly into esters, we can do using conditions that look simple, deceptively simple. The mechanisms are actually quite complex for this. And I'll show you as a set of conditions that you can use a mineral acid, so not an organic acid like a carboxylic acid, but a mineral acid like hydrochloric acid or sulfuric acid. I think the book tells you you can use both and then uses sulfuric acid most of the way. In my experience, I found HCl gives better yields. But again, hydrochloric acid or sulfuric acid. And then if you want to make a methyl ester, you use methanol as the solvent. If you want to make ethyl esters, you use ethanol as the solvent. But you need the alcohol to be present in big time excess as a solvent. Okay, we'll teach you another secret reaction for making amides. We're going to tell you how to take carboxylic acids like this and directly convert them into amides. You just take an amine. The recipe is just stunningly simple. So in this case, we would take an amine that has an H on it. Right? If I want to make a dimethyl amide, I need to take dimethylamine, and I need to add one extra reagent that you have not seen before that we'll talk about. And that reagent is DCC. Not PCC. PCC is for oxidation of alcohols. This is DCC, and you have never seen it before. And it's just so simple to make amides using this recipe. And we'll talk about DCC later because you've never heard of that before. Okay, we're going to talk about anhydrides, carboxylic anhydrides, where you have kind of two carboxylic acids joined together through a central oxygen. And we use those when we want a cheap acylating reagent that you can buy very cheaply. In this case, I'm showing you how to pop off one of these. In this case, half of this is always going to be thrown away when you do these reactions with anhydrides. In this case, it would be, I guess, the right half that gets thrown away. And we're going to make an amide using aniline. And so the reagent that you need here is aniline. Let me go ahead and write that out. H2N, pH, or you could write it PHNH2. And in this case, we're going to generate acetic acid as a byproduct. And we don't want the reaction to be all clunked up with acetic acid at the end, so we add a base to neutralize that acetic acid. And the base we add in this case is going to be triethylamine. And I don't think you've seen that used before. I'll show you some cases where it matters what base you use, and in this case we use a base called triethylamine. And I'll talk later about the relative advantages of triethylamine versus the kinds of bases that you might have seen before, sodium hydroxide or pyridine. But this might be a new one for you, triethylamine. Okay, we're going to learn how to take esters and cleave them. Boy, so easily, so fast, room temperature. This is the way chemists cleave esters, this method right here. We take sodium hydroxide, and that's it. We just take sodium hydroxide. It could be an aqueous solution. You just take sodium hydroxide and it cleaves the ester. And you can kind of see it doesn't give you a carboxylic acid. It gives you the sodium salt, the carboxylate anion. If you want the carboxylic acid, you have to work that up with HCl and stick a proton on there. But the reaction is so fast and so efficient and occurs at room temperature, and you don't have to heat things or reflux things or do anything like that. Okay, this is only half of the functional group transformations, the recipes, that I expect you to master as tools so that you can work problems on my exam.